Okay, so we covered magnetic inductance by going through a sort of kind of like little workbook in class. There was not a lecture attached to it, and you had it in lab before we did it in class. So I had assumed that there was some kind of decent exposure to it, and we could just try to work through it rather than you listen to me do it. Because, as you saw, this is a hard topic. Even I made a mistake when we were doing it the first day. So, but then when we were doing the problems and working on these review sections for the final, I feel like we could benefit from seeing more examples. So the whole point of this is we're going to do examples, 3 kind of qualitative, 3 quantitative, or 3 I guess kind of analytical magnetic induction problems. So first thing to review is magnetic flux. As we saw with Maxwell's equations, right, it's really the time derivatives and the changes of magnetic and electric flux that tie into a lot of the stuff that goes on in Maxwell's equations. Flux seems to be a very important property, something we should be able to calculate. So it is defined as the integral of the magnetic field dotted with dA, and the idea here is that you have some surface. Let's draw it as a parallelogram. And there is a well-defined area for this surface. Here I just drew it as a flat plate. So the area is very straightforward. Let me highlight this area. It is 2D, so I can write that it has total area, capital A. And the idea is that if there is a magnetic field that is going through this region, maybe like something like that, that is B. We'll treat it as uniform to make our lives simple. We want to calculate the magnetic flux through this particular surface. Let's see. This is uniform. There we go. Right, because there's field lines also around it as well, and behind it, and all that stuff. And if you think of, the kind of 0th order approximation we made for electric flux is it's counting field lines. And then we upgraded that to say that's not just counting the literal field lines, but it's counting the components of those field lines that literally pierce the surface. So maybe we'll just redraw that. So if I have some surface, if I have some little surface here, then I'm going to draw just, let's draw one magnetic field line. I'll have it go through the center. We can define the surface, particularly we can define the orientation of the surface by a normal vector. So the normal vector we're going to use, I guess since I shaded in red, maybe I'll use dark red as the normal vector. It is a vector that makes a perpendicular angle, or is perpendicular to the surface. If it's a uniform surface like this, then that one vector really is representative of the entire thing. If you have something like a sphere, then each little section of the sphere would have its own little normal vector, right? You look at things in the calculus limit in that case. We're going to stick with simple geometric surfaces in this case. So this red arrow, this normal vector, again, the idea is that you can have dA, which is the kind of calculus limit normal vector such that the integral of all these dAs, which is a vector, So I should say something about the components of this dA. I'll write down the answer first, is equal to some vector A, where we will say that for vector dA, the magnitude is just dA, and it points perpendicular to the local surface. So if you are considering something where it's like a sphere, for example, those arrows are constantly readjusting themselves based on where you are on the sphere. So that's why I say it points to the local surface. When it's a kind of simple geometric shape like this, you can get away, instead of doing dA, you can automatically skip to A. The idea with the magnitude here equals A, which we defined above, the total area. And it still points perpendicular to, in this case, I guess the entire surface in a sense. If you're able to do that particular integral given the definition of magnetic flux. So then when we have something like this, where we have a magnetic field line, and then that's kind of curled up there. And then we have a normal vector, which I will define, draw it right down the center. And we are trying to ask ourselves, what amount of this particular field line pierces the surface, which means it goes through. Well, it's not too hard to see that this vector for B, label B, and dA, that there is a component of B that is perpendicular to dA, and then there's a component here that is parallel to dA. Or you can think of it, instead of the dAs, you can think of it as perpendicular to dA, or it is the B that is parallel. I might even say something like tangent, where B is the B component. No, let's stay with parallel. Parallel to surface. In this part here, it's one that's parallel to dA, or it's the B component perpendicular to surface. Should probably give them different colors. I'll use the highlight. So if we highlight the one in the bottom and look at just that first, this vector, or that component rather, is perpendicular to dA, but I think where it's telling is that it's parallel to the surface. It's tangent to the surface. It doesn't actually go through the surface. So in this case, it does not pierce. Surface. While the other component would be too much blue on blue. Whatever, I'm in too deep. That looks terrible. Maybe a lighter highlighter. There we go. Where this component does go through the surface. that is what we want to count for the magnetic flux. We want to count all the contributions of the stuff that is actually going through the surface. It perhaps then is not too surprising that the magnetic flux is defined using a dot product, because I don't know if I defined it this way in this class. It's how I start and define the dot product in upper level mechanics. But if I do something like, if I have a unit vector, well, we've seen this enough. I don't have to go through this from scratch. All right, so remember that the dot product extracts. So dot extracts. And we could do it one or two ways, depending on what makes the most sense for the problem we're trying to solve. Extracts component of B parallel to DA. Or you can think of it the other way around, where it extracts component of, so dot dot dot, component of DA parallel to B. Right, the dot product is, you can think of it as pulling out the component B parallel to A, or the component of A parallel to B. So in this case, the magnetic flux, we just think conceptually, B dot dA is then equal to the integral of the B components parallel to dA times dA. So since this is the piercing component, this ultimately is adding up the contributions of the field lines that pierce the surface. We don't have to worry too much about that, other than how we define our normal vector, but let me come back to that after we write down some basic definitions of this. So if I define the flux as B dot dA, I'm kind of now too far away from this picture. So, we'll just have to redraw it. Let's see, I guess we got equations on the left, some drawing concepts on the right. So if I have some area, I'm going to define a surface that is going to be the surface I'm interested in calculating the flux through. Notice it's an enclosed surface. Can you have a non-enclosed surface? No. Right, there's some overall area associated with it. So I'll write this as dA. And again, it is perpendicular to the surface. And then I have B, which goes like that, using the dots to mark what's behind. There's B. Then there is a well-defined angle between these two, theta. And then we're off and running with the dot product. This then is the integral of B cosine theta times dA. I rearranged it a little bit because again, B cosine theta, what's that? That's the parallel component, the component that is parallel to dA. That's the same thing as the integral of B parallel to dA dot dA. I guess not, well, it's fine, these aren't vectors, I couldn't say dot. I'll try to reserve saying the word dot when I mean dot product. I kind of did that there too. Okay. All right. So notice in this case, for a given normal vector, which I'm going to use dA, I think your book, an expert TA, uses lowercase n. I know other books use that too, because I can always define, if I make a copy of this, right, and look at it, we have this normal vector dA, which has, again, magnitude dA. That essentially becomes what you can then integrate over. And direction, we just, I guess, are saying it's perpendicular to surface, which sometimes we use lowercase n to specify that unit vector. So I guess like e.g., the notation I've been using is dA, so it might be dA unit vector. And here, this dA for the magnitude, again, is the magnitude of the vector equals just dA. And then this unit vector, of course, gives you the direction. So, in this case, it simplifies nicely when the magnetic field itself is uniform across the surface. So if B, the vector, is uniform across surface, right, and this is a surface such that the angle between the vector B and the vector dA does not change. I guess as you know, anywhere on the surface might change with time, but it does not change anywhere on the surface. Then, and let's state if B is uniform across the surface, well, we can just do it. Then this integral of B dot dA is then going to be the same thing as the integral of B naught, we'll call that the magnitude, times cosine of theta times dA, the magnitude. Okay. Sometimes I gotta put a dot, sorry. Cannot stop my muscles. So if B is a constant and theta is not changing, then that cosine acts as a constant. So then this looks like it's B naught cosine theta integral of dA. Integral is a fancy word for sum. So it's saying add up all these little differential area elements. Of course, then that's just going to be the total area A. And then we essentially go backwards with the definition of the dot product. And it looks like this is just B dot A. Some vector A, which I don't believe I defined above. I guess I did right there. Right, so that's the integral of dA is A. Magnitude is the total area. Direction is the kind of universal normal vector. Okay. So, and some diagrams that we are not ready for. So, where this is important is that we have a time derivative of it in Faraday's law of induction. So, we are curious about d phi by dt, or more generally, that there is some change in flux. The whole point is that there is a change in the magnetic flux through the surface, or more generally, we want to calculate I'll just write it as why I'm writing in blue will become clear later on, a delta phi b. We want to calculate a change in flux. How the flux changed. Which, if you can take a derivative that has within it that information, the derivative is telling you how something changes with time. Or you might have kind of point A and point B, or start and end. And you want, if you just take end minus start, you're essentially calculating an average change for that particular quantity. Okay, now let's talk about the sign of magnetic flux. When is it positive, when is it negative? Well, we can use our knowledge of the dot product to figure this out. If we look at the integral of B dot dA for a surface, and then I'm going to replicate the surface. A great replication. And I want to calculate the flux through this plate. But you may appreciate that there's essentially two ways I can write down a vector that is perpendicular to that surface. I could write it down as this vector like we had before, call that dA. Or I could have it start at the same position, go down, do this. The dots kind of show you what's happening underneath. It's perpendicular to the surface, but underneath. I could call this dA. Is one more correct than the other? And then perhaps I have my magnetic field, which I'll use that same vector. So it looks like this. Same thing going on here. Down. So in this case, it's all in that cosine factor. So here's the angle between these two vectors. Then this one has an angle that's much larger. I'll call this theta 2 and this theta 1. And if you stare at it long enough, and let me just copy the magnetic field line. And then if I had dA, I'll call it dA1, and then this dA2, then this angle is called theta 1. And then the other unit vector, which, sorry, not necessarily unit vector, sorry, the other dA, which then creates a different angle, it too. By advanced mathematics, it looks like those two better add up to 180 degrees, or pi radians. And that's going to play an important role in a second. So when I look at the cross product, what I do, just kind of some general thing. So if I have, what letters are we using? C dot D equals, again, the geometric definition is that it's the magnitude of C, the magnitude of D, times the cosine of the angle between them. If I just think about what cosine looks like when I plot it, it starts up here, comes down, loops back around, starts over. So this is 0, this is pi over 2, this is pi, 3 pi over 2, 2 pi, and 5 pi over 2. This angle. And this is the value of cosine theta. Which you cannot tell that is what it is because it's smeared in with the axis. So in this case, it looks like, and then we have to think for the dot product, we can restrict ourselves even more. For the dot product, we don't care really about anything past 180 degrees. We only really care about the region, right? The angle for a cross product is somewhere between 0 and 180 degrees. So again, this is the plausible region, plausible theta values in dot product and in the cross product actually. So in this case then, it looks like the dot product, since magnitudes are always greater than 0, I'm assuming these are non-zero vectors, else it's a pretty boring problem, that the only thing that can determine the sign of the dot product is this cosine factor. So the cosine factor is greater than 0 when theta is between 0 and 2 pi, and it is less than 0 when it is between pi over 2 and pi. So, or said another way, the dot product is positive. I'll do over here. Dot product is positive for 0 less than theta less than 90 degrees, 0 degrees, and then C dot D less than 0, where 90 degrees less than theta less than 180 degrees. So things that are closer to being parallel, positive flux. Things that are closer to being anti-parallel, that would correspond to a negative flux. Now the nice thing about flux is that it is your choice in terms of which normal vector to use. There are sometimes conventions, like if you have a closed surface, so something that encloses a finite volume, you can, the convention is that you pick, the normal vectors point away from the volume rather than into the volume. But for just like a sheet, something that's not a closed surface, you can pick the direction of TA. Really, by choose direction, right? It's, you have two options, from the two options. In my humble opinion, I don't think that's what the H stands for. I'm going to say it stands for humble. In my humble opinion, pick the one that has which then gives you positive numbers for flux. It's much easier for me to deal with positive numbers than negative numbers. So pick the dA that will give a positive magnetic flux. Since what we're going to be focusing on is that induced currents result from the change in flux, again, as long as we are consistent, right, I can't make my dA vector point one way and then halfway through the problem change the direction it's pointing unless the actual surface flipped upside down. As long as you're consistent, I say try to work with positive numbers. That makes my life at least a lot saner. So if I go back to these at the bottom, I'll just copy them. We haven't quite made use of the fact that those angles are complementary. Along some highlighting. So let me separate these. So in this case, this one on the left, they are closer. If that's what I defined my dA to be, I said here's a slab, and I'm going to have the dA vector point up. Right? This is closer to parallel, which implies then that the magnetic flux, well, I mean, not skip the intermediate step. It implies that the cosine of theta will be positive, and then that implies that the dot product will be positive. And then since I'm integrating over a bunch of these, that implies that the magnetic flux will be positive. And then I think you know what's going to happen here. In this case, then, it is closer to anti-parallel. Which means that the cosine is negative, which means that the dot product is negative, which means that the flux is negative. And again, these are for kind of simple surfaces that it's essentially this it's a sheet. If you have a curved complex surface, then different parts of it, as you integrate over it, might have some of them might be positive, some of them might be negative. But in this case, the angle between the normal vector and B is the same everywhere on this sheet. So that's where we're making these simplifying assumptions. Now, if I say you're allowed to choose which of these you want to have the normal vector, but that the flux is changing, one's positive, one's negative, right? It should make sense that the magnitude should not be any different between the two. So really, it seems like the only difference should be that one has a minus sign. And this is not too hard to prove. So again, if theta 1 plus theta 2 equals pi radians, then that implies that theta 2 equals pi minus theta 1. And so when I evaluate the dot product let's call this case 1, call this case 2. So for case 1, the dot product is equal to the magnitude of B, the magnitude of dA, and then the cosine of the angle between them, which we said was theta 1. And then for case 2, the dot product is equal to B dA cosine of theta 2 is equal to B dot dA times cosine of pi minus theta 1, and the trig identity is exactly what we want it to be. That, let's draw it up here. This is not too hard to prove, and this doesn't really constitute proof, but I'm going to give you a sense. Here is cosine. So if the black line is showing kind of cosine of theta, and when theta is 0, you're here, and then you kind of step forward in this direction as theta increases. As I guess theta increases. And then if you think about blue, cosine of pi minus theta. Well, when theta is 0, you don't go up along the y-axis, but you start out here, right? Cosine pi. And then as theta gets bigger, the argument inside the cosine gets smaller, so you're kind of tiptoeing your way that way. as theta minus pi decreases as theta increases. And you can notice that kind of the shape of the cosine, for the red is the same kind of shape for the blue, but there's a sign flip. And put that up. This is just simply dA cosine of theta 1. Where the trig identity is that cosine of pi minus theta is equal to negative cosine of theta. So indeed, let's highlight some things. The dot product in case 1 was this. The dot product in case 2 was this. They are indeed the same magnitude, but only differ by a negative sign or directionality. So in this case, if you're choosing positive flux, right, you can choose one of those that will give you a positive flux, which again I think will make your life a lot saner when we start looking at how things change, because we should remind ourselves about the number line and change. So if I go, let's just think of a 1D number line. And let me do a couple examples. The number line, of course, it keeps going in both directions forever. And so if I have, and then this is 0, this is 1, 2, dot, 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 negative 1, negative 2, dot, dot, dot. So sometimes the wording is confusing, because when I say I go from, let's just give this a variable, let's give it B. If I say B goes from 0 to plus 3, then delta B in this case, we would say has increased. What is it? Delta B, how would we quantify the change? The magnitude has increased. If B goes from negative 1 to 3, positive 3, then I would say again that B has increased. It's going in the direction of the positive numbers. If you go from plus 3 to 0, then delta B has decreased. And here's where I have to be careful. If I say you go from negative 1 to negative 3, the number is bigger, but I would say this is yet again a case where delta B has decreased. It is in the direction of the negative numbers in this case. Because I think it's easy to get confused where you think like the closer it is to 0 is when it's smallest, or really, I would say of all the numbers I've written down, negative 3 is the smallest number on this 1D number line. Right, and I'm writing a lot more than I drafted in my lecture notes, so all these diagrams are going to keep getting punted. That's alright. It's good to do this carefully. So, essentially, with the 1D number line, when we're looking at changes, towards positive numbers will be increase, towards negative numbers will be a decrease, and that will be important. So, again, and now with this understanding of how we can talk about whether or not the flux increased or decreased by thinking about it on the number line, we have to think about when and under what conditions will we say the flux increased versus decreased. I've been saying that when the magnetic field points in the same direction as dA, you get a positive flux, and then when that number gets bigger, that's increased. When that number gets more and more either closer to zero or then more and more negative, it's decreasing. Let's make sure we have an understanding of conditions when I say that the flux increases. Let's actually stick with flux variables. So if d phi by dt is greater than 0, that means that the time derivative of this integral is greater than 0. Thinking about it in terms of field lines, more field lines are going through the particular surface. The surface itself may be changing. There might be other conditions in which it's causing this flux to increase. Let's think of it in terms, let's anchor our intuition in terms of the magnetic field. If the magnetic field is getting stronger, which by that means that for a given direction of the magnetic field, it's increasing in magnitude in that direction, which could be parallel, anti-parallel, perpendicular to dA. By saying that the overall flux is increasing, right, that means that, again, thinking of the number line going towards positive numbers mean B is the flux. If the flux being positive means more parallel towards dA, that more field lines, if you want to think of it in terms of that sort of viewpoint, an increased magnitude of the flux, or maybe some other alternative viewpoint, is happening in the same direction as dA. Because dA is what is defining the positive direction when we talk about flux. So for example, if I have some sort of surface, which I'll approximate as some circle on its side, some radius r, I don't really care, and the surface I'm interested in, shaded here in red, and I'm going to define my dA vector as such. I'm making a choice that the way it's going to point is up. Because then if I have a magnetic field that is pointing closer to parallel, so actually we can even just make it parallel, since I'm just trying to use this as an illustrative example. So I have a field that is kind of going up in the same direction as dA. All right, if the magnetic field, for example, is increasing in magnitude, so I'm going to write if d by dt, the time derivative of the magnitude of B, is greater than 0. Right, that means if B is pointing this way originally, and at some later time it might be going like this, some later time it might be going like this, is increasing in magnitude, is not changing its direction. Then, since dA also points in that direction as well, that implies then that the flux is greater than 0. Or if we think of it in terms of a delta, the delta flux over delta t is increasing. Or it's positive. You want to think of it that way. I'm going to try to stick with this kind of increasing, decreasing. Now the flux is increasing. So the derivative is, yeah, really the grammar's a little off here. So I might say that if delta phi is increasing, no, that still doesn't work, right? If I'm saying that the delta phi is positive, then the total flux is increasing in that there is more flux in the direction of dA. Going back to that picture on the left, more field lines going up, that would be an increase in flux. In this case, the change is positive, the total flux is increasing. If the magnitude was shrinking, so that could be example 1, example 2, if the magnetic field is pointing straight up, parallel to dA, and I say that the time derivative is less than 0, then that might be something where this is B originally, this is B at some later time, B at some later time, and maybe it even turns around. And that's at some other later times. In this case, then the time derivative of the flux, I would say, is less than 0. The change in the flux is negative. Or that the total flux is decreasing at all of these points, in that there is more flux anti-parallel to dA. I'll just alter this, more flux in the opposite direction of dA, or it's anti-parallel. As examples of how this can appear, so that we don't get it confused. All right, my drawings have now made it to this page. Just gotta make a new page entirely. So then we could ask ourselves, well, first, let's finally now connect this to physics. Let's connect this back up. Why do we care so much about how the flux changes? Well, you have seen this already, but this is, of course, Faraday's law of induction. And that it's not the presence of a magnetic flux that creates an induced current, but it's the changing magnetic flux that produces a current. So it is usually written as the induced electromotive force, or EMF, or I like oomph, is equal to negative the time derivative of the magnetic flux through the surface enclosed by a circuit. You still need a completed circuit for this to work. I can't just hold a wire that's just open on both ends and expect to wave a magnet nearby and current starts flowing through this wire. It needs to still be a closed circuit. That then defines a well-defined area that is enclosed within that circuit. That then is the surface in which you evaluate the magnetic flux. So, for example, just to give an example of this point on the right, that suppose you have your ammeter, one of those old school ammeters. So, little 3D device here. Here's the reading. Here's your arrow that's pointing to some current reading. Here's your ports for the wires. One of them's positive, it's red. Then you have your wire, which is this kind of gray thing. And it kind of goes out and it kind of wraps around and then goes back in. That's it. Well, this is a circuit, a completed circuit, in that there are devices, there are conducting wires, there's no battery. That's okay. There's still a well-defined surface here. Current is not going to flow naturally unless we could somehow measure a changing magnetic flux through that loop, maybe by waving a magnet nearby. We would notice that then a current is registered on the ammeter. So this is the example of a wire completing a circuit. And then this is the surface enclosed. Just a little aside. Faraday's law of induction, of course, is saying that if there is a change in the magnetic flux, there is an induced current that acts to oppose that change. That is what's called Lenz's law. That's what really this negative sign is doing. This negative sign is saying a lot. Lenz's law, which says that the induced EMF acts to oppose change. Right? There is some magnetic flux at the start of things, and then if it increases or decreases or whatever it does, the induced current will act to counteract that change. It likes the good old days. The good old days where whatever the flux was at the start of things, it wants to try to return the system back to that. Kind of a magnetic inertia. In that, what I think is useful to think about here is that we write this down because this formula gives us a way of evaluating the magnitude of this induced EMF, this voltage, which then will drive a current through a circuit that might have resistors and whatnot. But really, what's creating this? It's opposing the change in the magnetic flux by creating a current, which therefore then creates a magnetic field, which acts to oppose that change in magnetic flux. So, again, as an example of how this looks, suppose I have a circular conducting loop, and therefore my well-defined surface is region within it. I can define my normal vector as pointing up, and I'm going to do that because I know that the magnetic field is also pointing straight up, and I'd rather deal with some positive quantities. There's B. So, if, for example, right, we'll go through a more systematic way of figuring all this out, but just to give a quick overview example. If the time derivative of the magnitude of the magnetic field was increasing, then I might use two different colors. The blue I've been using, maybe like a dark blue. And the dark blue is going to represent the magnetic field that's, say, around in that region 10 seconds after the start. Then if this color shows the magnitude of B at the start, with this kind of darker blue showing the addition to the magnitude of B by the end, then in this case, by the way I've defined the light blue and the dark blue, the kind of average change is everything you see in dark blue. Then the dark blue is also showing the change in B, and the average change. They didn't say how long this took place over. So I'll say that as some sort of delta, the magnitude of B, the change in the magnitude of B. So in this case, I would say that, if we stick with the dark blue, that the kind of delta, the magnitude of B, is positive, in that there is more magnetic field lines pointing near parallel to dA, so which that implies then that the magnetic flux is increasing right, or you can say that the change in the flux, the delta flux, is also positive, which again, by saying that the flux is positive means that it is the change is in the direction of dA. By saying the delta, that the change in the flux is positive means now there is more flux in the direction of dA than there was at the beginning. Lenz's law, which I might use as red. So Lenz says that it will create an induced EMF to create, or just write it all out, to create an induced current to create an induced magnetic field that loops around that current to attempt to cancel out not the flux entirely, but the change in flux. In this case, so B induced will point, if dA points up, well, I'll just write, it will point anti-parallel to dA. Since the delta flux was positive, the flux was increasing, it's going to want to counteract that and make it decrease back to what it started with. Again, once the good old days. Right. To cancel out, I'm being redundant. We'll create psi to create I to create B to cancel out the change. So it will be, yeah, that's how we've done it. Maybe I shouldn't use red. I should use maybe green for stuff we're going to do here, since I'm already kind of using red for the surface. So I'll use green to cancel out. So then if we go back to this drawing, so we're going a little busy, so maybe I'll just copy and paste. And so as a result, what happens is that there is an induced current, or so we could work backwards now. Psi creates I, which creates B, and that B is intended to cancel out the flux. So we could ask ourselves, what direction does this induced current have to, or sorry, this induced field, if it's going to cancel out this change, and I can just write green arrows that are always opposite the change in flux. So the induced is all pointing that way, inside the loop, or on the surface, or through the surface. And then we can use the right-hand rule. What direction of the current through this loop will give me the green field lines? So if I have, right now colors to use. So if I want to create field lines that loop around the edges of the loop, because I know if I have a current carrying wire, there are loops of magnetic field around it that can be understood by the right-hand rule. My thumb points in the direction of the current, my fingers on my right hand curl in the direction of the magnetic field. If I want to create the green lines inside the loop, it seems like I have to be going in this direction. So that would be I induced. And it kind of goes in this direction, I induced. Because again, if I have my thumb follow the arrow, my fingers curl into the loop, and then curl back up outside the loop. That would then create the green field lines to counteract the change in flux. So then I induced is in that direction based on my drawing. And so that then tells us kind of what the IMF, or EMF, sorry, IMF, that's astronomy, must be. If I want a current that kind of flows in that clockwise direction, I can imagine that makes the circuit, something, maybe there's a resistor, but there's some induced EMF that I'll represent here like a battery, but it will then pump current in this clockwise direction. That is Lenz's law. Well, that is kind of a combination of Lenz's law and Faraday's law of induction. In this case, really, if I want to ask myself what is the magnitude of the induced EMF, right? The magnitude of an EMF is really only positive. So to set it equal to negative the derivative, I think sometimes some find that confusing. I might say that the magnitude of the EMF is the absolute value of this time derivative of the magnetic flux. Whatever you get, just the positive number then is the induced EMF. You do have to be a little bit careful if you have a function that maybe the induced EMF can change signs. Then the negative might be meaningful, and in which case you want to just make sure you're explaining it in a way that's correct. Right, so I might say kind of caveat, unless your change in flux is switching between increasing and decreasing. You can of course still use this to get the magnitude, but then you just have to take a little bit of extra care to make sure you're getting the directions right. That negative is really just saying, here's how you figure out what direction, right? You want to oppose change. You want the good old days. And this really comes down to that there is a time derivative in the magnetic flux. So I could ask myself, since we are going to be evaluating the change in the magnetic flux, how do you change the magnetic flux? This is important, and I'll do some examples that demonstrate all of them. How do you change? The magnetic flux. I think it kind of comes down to one of three ways. And again, let me rewrite the definition. Magnetic flux, magnetic field dotted with this dA element. If the magnetic field is kind of uniform in that region, such that the magnitude of B and the angle between B and dA is not changing with time, this becomes B dot A, which of course is B A cosine theta. And this really kind of shows you the three ways that the flux can change. One, the magnitude of B can change. Is the field getting stronger? Is it getting weaker? That could be as a function of time. That could be as a function of space. Like maybe you have a pendulum that's just a loop of coil, and it's just swinging back and forth. And sometimes it swings into a field, and sometimes it's not in a field. You can imagine there the magnitude of the flux can change because of the changing overall magnetic field in the area. The area can change. That might be like problems we looked at in class. You have some conductor rail that is connected to, some railing, and this rod is moving with some velocity v, and everything's conducting. So you have this kind of well-defined circuit here that as the right side kind of moves across the railing, that shaded area will only grow. That could change the magnetic flux if there's an overall magnetic field in the area. Or the orientation might change. Maybe the field rotates. Maybe the circuit rotates. My pendulum comment. That is going to then change the amount of field lines that is going through a surface if that surface is changing its orientation in space. So, in this case, we are ready to now kind of start looking at examples of how you, by changing the flux, you do see a current, and how we can make sure we can very systematically figure out what's going on. It comes down, I think, a lot more to kind of, if you have a well-defined dA, then that tells you kind of what positive and negative is, and as long as you follow the steps, you're gold. So, let's see, I'm close enough to the end of the page. I'm still gonna do this. So the goal now is to do just a handful of examples. I'll do examples until I'm just blue in the face. So examples of Faraday's law. Undoubtedly probably one of the more challenging things in this course, because not only are you dealing with this kind of abstraction of flux, but it's not the actual flux that you care about, it's the change in flux that you care about. So, let's see, I have some drawings that I'm pulling from the worksheet that we had. So, move those over here, and then we can talk through them. All right, so here's our first example, which really will just lay out the algorithm. Example 1, you hold a magnet stationary near a circuit. In this case, in order to evaluate an induced EMF, which evaluates an induced current, which you can evaluate an induced magnetic field around that current, which then creates the magnetic field in the flux that tries to counteract what is changing in the first place. Here is the drawing for those of you who are not in class, or not part of this class, of how I will demonstrate this. This uses our coils. So I have kind of one of these old school ammeters, and it is hooked up. We won't actually care about the direction of the current that much, but it's hooked up in such a way that if current is kind of flowing clockwise through that coil, that is a positive current, and then if current is flowing kind of this way through the coil, that is negative current. So again, the idea here is that I have an ammeter that has a wire that kind of travels here. Well, really, if I take this, the current kind of flows in that direction. That's the quote positive direction, and then it's just kind of going from minuses to plus, and it's kind of creating you a complete circuit. What the surface now I care about, because I said, even just having wires laid about will create a surface that you're evaluating the magnetic flux through. But in this case, if you look at the backside of our coils, it says that the actual wire in there is wrapped around the coil like something like several hundred times. So while yes, there are wires here, and you might think there's a little surface there, a little surface there that we have to measure the flux through, since the wire wraps around so much, if it's 500 times, that then is a factor of 500 that we increase whatever we want to discuss through this particular coil. So in that case, the coil dominates. Well, maybe I'll just write that to the side. Using our lab coil, it dominates in the circuit. So when we're considering things like flux, really that's the only place we have to look. We really only have to look at the surface here that I've shaded in red. And what's going to happen is that I'm going to hold a magnet kind of along that central axis, that cylindrical center of the coil. I'm just going to hold a bar magnet along that central axis, and it's going to be stationary. By doing that, I then can imagine the magnetic field lines that are coming out of the north side of the magnet and then are re-entering in the south side. And some of them are looping around very close to the magnet. Some of them are going farther and piercing through the surface. Some of them are going even farther and might loop back around kind of way out here. Again, one of the first steps I want to do is I want to define how I'm going to evaluate the flux. Essentially, I'm asking which direction am I going to use as the positive direction, the increasing direction. Increasing means more towards the positive. That's defining my number line in a sense. So I'm going to maybe call this, should I try to give it steps? Oh, why not? Well, I'll just use bullet points. So here I'm going to define my vector dA. And again, what this is doing is it's defining the positive direction. Since if I look at the magnetic field, the flux or the magnetic field is kind of going this way through the loop. And I know positive flux results when dA and the field are closer to being parallel. I'm going to define dA to also point in this direction. Then, when I look at particular field lines, notice in this case, there are many different field lines and they're kind of all going in a slightly different direction. Like I kind of see how many have I drawn, kind of like one here, that's where it pierces, one here, one here, one here. Like I've kind of drawn 4 representative field lines. So the one kind of on the left is kind of going this way because it's about to wrap around. The one that's kind of this way, or the second one from the left, a little bit more straight, might be going this way. And then by symmetry, essentially, then these do the reverse. These two at the end are not quite that extreme. Like that. And of course, this is all being compared to dA, which if I draw the circuit, just in case, is what they were looking for. See, I don't quite want a circle. So give me an ellipse. There we go. There you go, something like that. Because we've decided that this is my shaded region between the 500 loops of coil. And then for each of these, right, if we decide that these DAs cannot point in different directions, we're just going to have to something that looks like that. In which case, because the magnetic field is changing, the angle between these two things is different in different areas. There, you need the language of calculus to do the integrals, but overall, since these two vectors are closer to being parallel than they are to being anti-parallel, so essentially B and dA tend towards parallel. I expect the flux to be a positive number. Of course, it's not the actual magnitude that matters, it's how it changes that matters. So I'm going to define dA. We've done that now, and I've kind of added that to the drawings. Then at the start, we're not moving a magnet, so it's not actually going to be that impressive. Then at the start, there's some initial magnetic flux. I'll call it phi b dash O, or comma O. This is the initial state. We want to then measure, and I'm going to use blue as kind of delta phi, or what really is, the case, right, that we're measuring some sort of estimate of the time derivative of the changing flux. Maybe again with a negative sign, that just tells us direction. So again, even though I cannot evaluate a particular sum for say this particular magnetic field that's going through the surface, where each arrow is at a slightly different angle compared to the normal, that might be okay as long as by looking at these, I note that it is going to have a positive flux. In the state, the interstate measure. Well, that can't be right. I have to take this back. How can I measure a change if it's one of the first days? Right. Then at the state, the initial state, I'm going to say more as in calculate the state of the flux, the initial state. So to compare to, maybe it's phi b slash f for final, or you're looking at some delta flux, which maybe they don't give you the start and end, but they give you the delta. You might actually have access to the actual derivative of the flux as a function of time. That might give you a sequence or some sort of function of time, etc. I think that's more or less it. So by defining dA, we've decided which direction is the positive direction. And you get to pick. I'm not saying there's a right answer. I'm saying that you can purposely have so that the flux is negative if you wanted to. Again, I say working with positive numbers is much easier. Come on. So, in the case of the stationary magnet, you should notice that there is no induced B, there is no induced I, and there is no electromotive force. You also have to think about when the flux is changing, right? If I have this loop of wire, and say on camera there's a magnetic field that points out of the page, and I have the loop over here, and then it gets into the page and then does this and then gets out of the page. The only place where there's a change in the flux is when it's passing through the edges. Otherwise, it's just getting kind of the same ambient field until, again, it gets to the edge. It's just to lose some of that flux. The flux decreases. I guess it tends towards zero, which is also the direction you would tend towards if you wanted to flip directions. So this dA will play an important role. Let's work through some actual interesting examples where I move the magnet closer to the loop as we do this. So it looks like that's this. So let's call this example 2, where you move a magnet toward the loop or coil. Then if we look at this, I don't know, it seems kind of small to me. Boop, ba-doop. That over, this over. So if you look at this, I think your intuition can kind of suggest what should be happening. That as I move the magnet towards the loop, really to make it more explicit, I'll say with north side facing the loop, then it seems like the magnetic flux is increasing as a result. I'm closer to the bar magnet. I have more field lines going through this particular surface. This gives me some sort of delta for the flux. So, by defining the direction of positivity, by designing the flux of the magnetic field to be greater than 0, comma, right, since B on average is closer to being parallel with dA. We can then talk meaningfully about what it means when I say the flux increases. So, and I'm depicting kind of a start and an end, so of course this is then going to give us sort of average. I won't need calculus to do this. So, if I define dA as I've drawn, so again, I have some sort of positive flux on the start, or there's some value for the flux, use S, there's some value for the flux, maybe it was a different group, that is an F. And it seems like there is some sort of increase, so I'll redraw that with the color code I established above. But there's this delta phi B that when I take the start and I add that to it, I get what I see at the end. All right, so this is kind of a result from just the conditions, the environment. Maybe we'll call this the environmental change. The kerning is out of control here. So this is measuring kind of environment change. Environment delta. And again, unsurprisingly, what's another way to define this delta? Well, it's just the final flux minus the initial flux. Right. With, again, this delta phi being positive, implying what? Implying that there was flux in the parallel direction of dA, now there's more in the direction of dA. I might call this more flux pointing towards dA. And you can look at this for, if the delta is a positive number, what does it mean? If it's a negative number, what does it mean? So, here's kind of some reasonable steps for solving these sorts of problems. So of course, first step is, I would say, is to define the circuit. Where is the completed circuit? The surface that you're measuring magnetic flux through. Test any devices you imply that you might be using. And I think that's it. Define the circuit, the surface, test any devices, etc. So that we could then define, with that surface, define our normal vectors dA. And again, in my humble opinion, do it so the flux is positive. So when I'm looking at changes and whatnot, I don't run the risk of getting as confused. So with dA defined, I can now measure the flux and say whether it's positive or negative at two different points in time. That allows me to then measure whether or not their change in flux is positive or negative. So I might say measure the magnetic flux, the time derivative of the magnetic flux, or you might not be doing derivatives. Maybe you're doing some sort of average change. So that'd be some delta phi over delta t. Or it could just be that you're really just kind of looking at delta phi, so B. Right? Is the flux increasing or decreasing over some amount of time, which if you knew that amount of time, you could divide by it. But maybe you just really care about the denominator. So, and again, remembering that kind of a delta phi that's positive is kind of pointing in the direction of dA. So you've made your measurements, you've calculated your deltas or your time derivatives. You can then kind of draw, perhaps, the change in the magnetic flux. Visualize it somehow. Maybe there's more field lines, maybe there's less field lines. So with the emphasis being here on the change that you're identifying. I guess I can use light blue. Draw the change in the flux, and then what do we decide on? Green. Then the induced magnetic field opposes or tries to cancel out this change. In this case, it gives I induced and something else. Why am I blanking? Oh, the electromotive force that's induced. Those are, I think, a sense of the steps, which I feel like we can elaborate now and build upon with some conceptual examples. Because when I say that the induced B opposes this change, well, let's go back to the previous step. I would say draw the change in the flux. I'll move that up to a light blue. Because that change in flux, of course, is just delta phi. And we can think of it like a vector. Where kind of delta phi that's positive points, right, is kind of parallel to dA. A delta phi that is negative you can think of as anti-parallel to dA. Pretty sure that's anti-parallel. Not too late. So that then tells you the change. Then the B induced opposes this change, which again you should be able to, this kind of delta phi induced is in the opposite direction. As kind of this original change in flux, because again it's counteracting this change. And again, this is where the examples are helpful. Let's return to this case. I'll start essentially from scratch without tangents. So paste. Take that. So we have, I don't know which example this is. So we have the kind of example of moving magnet toward the loop. Again, first step, I'm going to define my dA. Really, I've already done that. We define it so that the flux is always a positive number. In this case, I'm now going to measure this change in flux. So, U lower. U, I made too small. I feel it's too big. Oh. So in this case, if you look at this, I would expect that this kind of first picture, I lost the word start. Let's see. It's the starting condition, that's the ending condition. In this case, it seems like I'm starting with some initial magnetic flux, which I define to be positive. It ends with some magnetic flux that I also define to be positive. And particularly now I'm interested in what is the change. I could look at the difference, or I could again think of it as I have some initial flux, I add to it some flux, and then that equals the final flux. And again, it is this change that I'm most curious about, because it's the change that matters. Now I can go back up here. I've defined my dA. That then allows me to measure flux, changes in flux. In this case, really the kind of delta, the changes, are going to lie either along or anti-parallel to the axis that you're proceeding with this lab at. Delta changes that are positive, again, correlate to in the direction of dA. When it is negative, it correlates with the opposite direction. Okay, so far so good. So once I have a change, I'm going to draw it I'm going to treat it like a vector. I'm going to treat this kind of, I've been using blue, this kind of delta flux as a vector, where again it's going to follow the rules in the previous line, where this change is parallel to dA, right, if positive, and it's going to be this anti-parallel to dA if negative. So in this case, the flux is increasing. So here, the change in flux is positive because the overall flux is increasing. It was positive to begin with, and it's even more positive at the end. So then I'm going to draw this arrow with the idea that it's kind of situated in the direction of dA. Then Lenz's law, or then Lenz says that the induced magnetic field must point in the opposite direction. So we've been using green, so I'm just going to draw this green arrow in the opposite direction. So in this case, since the blue was parallel to dA, it's kind of green is anti-parallel to dA. And then I'm going to find the current that will allow me to then counteract this field. So let me copy this last picture, just so that we can have some sort of visualization. So in this case, all right, if I again use light blue to be the start, then the end, now the contrast is not quite as grand. The contrast is kind of that there's more magnetic field lines coming through the loop. dA is pointing that way. The flux is increasing, which means that the change, delta phi, is in that direction as well. The induced magnetic field wants to counteract that. Flux is increasing, meaning there's more flux down to the left. The induced B field, oh sorry, we said green. The induced B field, resize, must therefore point in that direction. And how do you accomplish that? Again, by the right-hand rule. Seems that if the current, hard to see, the current is going in this direction, that direction, I'm going behind all these things, that direction, that is the induced current, or also the kind of direction of the EMF. So you might also say kind of psi, comma, I. In that direction, by the right-hand rule, the induced magnetic field will try to counteract this change. And again, why does that work? Now we have too many field lines. So let's see, if I have a current that's kind of going like this. Where is this being drawn? Okay. Then again, the magnetic field, by the right-hand rule, my thumb points in the direction of this arrow, and then the magnetic field looks like it's kind of going out and then in. It's kind of way too busy for you to see what's going on. So allow me to redraw it. So we have the loop, and then we're going to just only draw this induced current, which is in that direction, with the idea that the magnetic field that it creates by the right-hand rule kind of goes out and up and then down. That's not really the way to think about it, because of the way it's oriented. Kind of goes out and around and then in and then out and around. Again, following the right-hand rule. Again, this kind of goes out, in, and it loops around in this direction. Not sure if that helps. Is again with the idea being that we want the induced magnetic field to ultimately point and match this arrow. Okay. So now we can try to do some other examples. What about the example where here we brought the magnet closer. What if we pull the magnet away? What should we have? Move everything that we don't need for that problem there. And here we go with the next example. So, example where you pull the magnet away. And so the setup is going to be something like, here's the start, and then here is the finish. So let's call this start, and call this finish. And I've already done a couple of the steps for us. Since I now have the way that the magnet's oriented is that the north is on the top and the south is on the bottom, notice that that creates field lines that kind of loop around. It comes out of the north and kind of loops around and might go into the surface this way, such that when I pull the magnet farther away, more of those loops are going to be completely contained behind this coil rather than going through it. There still might be, right, this one that kind of goes way out here might still go through in this general direction. So as a result, notice I made DA point in the opposite direction. So I could say for the first step, given the B field line directions, we're going to define the DA element. So the overall flux at the start is very much a positive number. So I'm dealing with positive numbers again. This required me to define the surface, which required me to define the circuit. I think we're kind of all set on all of that. So then I should have copied these directions to the other page. Right, we have DA, now we want to measure a change and then label that change in some meaningful way. So given B, the magnetic field, I'm going to define DA to be that way. So then at the end point, fewer field lines. Through the surface. They still would be going probably in the right direction, in that if I were to draw more magnetic field lines, right, the next kind of one that goes out might kind of do something like this. So it seems like they should still be going in the right direction through the surface. So I still expect the magnetic flux at the end, at the finish, to be positive. But if I think of the flux start plus this delta flux to equal the flux that's finished, it seems like the flux is overall decreasing. Again, positive is in the same direction as dA. I could even draw the kind of net flux, if you will. There's lots of arrows going through the surface, so maybe that's kind of the vector-ish interpretation of the original or the starting flux. Then at the end, there's fewer field lines going through, so maybe that's kind of a representation of the net flux. So if I just think of how I add vectors together, what vector do I have to add to that first vector to get the small little vector? Well, I have to cancel some of it out, so I might have a flux or a delta flux. It might look something like that. And then when I add this plus this, I get that. If I think of them as vectors. So let's see, I might even make a copy of this so I can move it down here to the text. And the delta is in that direction. So then what does that mean? That means then that the kind of magnetic field that's induced should point in the opposite direction. So this, it seems like the blue was anti-parallel to dA, because the flux is decreasing in that it's going away from the positive direction. The being induced should point in the opposite direction, so that arrow should point, be the flip. So this is then parallel to dA. That's all well and good. And then we just have to think about what direction the current has to be to do that. And it seems like then we have more or less the same as before. So in order to get the induced magnetic field, I should have made that green because we're sticking with green for induced magnetic field. If I go back up to the picture, it's not too busy yet. Essentially, I start with lots of flux going through the tube, and then there's not as much flux going through the tube. So wanting the good old days, it's going to create a current that's going to try to restore the flux to its glory days. So it's going to want to induce a magnetic field that points in that direction. You can get that if you have a current that goes in this kind of clockwise direction. Because then the field lines loop around, something like that. And by the right-hand rule, it kind of loops out on the outside and then in on the inside. And that goes to reinforce and restore the field.